In this unit, we've been examining the life cycle of stars, and we're going to take a few notes over that. So let's just go ahead and get started. We know that a life cycle of a star depends on its mass, how big it is. The bigger it is, the hotter it can get, which means it can carry out nuclear reactions faster. Smaller it is means it's going to be cooler, which means it carries out those reactions slower, and so it lasts longer. So our sun is a main sequence star. We'll talk about what that means in a minute, and it's average in size. It can have a lifespan of about 10 billion years. Because it's smallish, average to small, it lasts a really long time. Smaller have even longer lifespans. They're cooler, so they don't fuse their hydrogen into helium as fast. The larger stars, which are blue, and that corresponds to hot, which is a little bit backwards than we usually think, but that has to do with the electromagnetic spectrum, right? As you go across the rainbow, red, orange, yellow, green, blue, violet, you get closer and closer to this side. This is the more energy side, and this is the less energy side. So red has got less energy, it's happening slower. Blue has more energy, it's happening much faster. So they're huge, they're massive, they have more fuel, but they burn it much quicker. So let's take a look at a couple diagrams. The first one I'm going to show you is called an HR diagram, and it shows us luminosity, or how bright the star is, versus its temperature. Now, as you'd expect, brighter stars are hotter, and so this is hot over here and this is cool over here. The warmer it is, the brighter the star is. The cooler it is, generally speaking, the star is dimmer, although you do have this group over here of supergiants, and they are very bright. And the reason they're so bright is because they're huge. They're fairly cool on the surface, but they're giant stars. These blue ones over here on the main sequence, they're fairly little compared to these supergiants, but they are super hot and super bright, and the reason of that is they do have a lot of mass. Then as we move further down this main sequence, so this line's called the main sequence, we can see the stars get cooler, dimmer. The sun is right here. So you can see it's a low to average mass star that's not super bright. So it'll last us about 10 billion years. Now, these are remnants of stars. So these dwarfs over here, this is what happens when stars in this region kind of fizzle out. They run out of fuel, and eventually they'll turn into white dwarfs. These things are what happens when these stars run out of fuel. They move over into the giant and supergiant stage. So we can take a look at that in the next diagram. Every star starts as a protostar. Doesn't matter if it's a supergiant, huge, massive star, or if it's just an average sun-like star. They all start as protostars in a nebula. Gravity contracts, causes this start to glow because of the energy that's being produced in the collisions. As it gets warmer and warmer, nuclear fusion occurs, and then we get stars. For the low to average mass stars, we go to a giant. Then it ejects its outer matter because of that last thermal push, and the core eventually cools off into a white dwarf, finally a black dwarf. For the more massive stars, it follows a similar path all the way to the end. If it goes supergiant, then it goes supernova, which means it explodes. There's lots of energy here, so it's got enough energy to explode. There will be a core left over, and inside this nebula, so this is all the junk that comes out of the star when it explodes. That can be recycled into more stars. But the core that's left over, if it's not too massive, it'll be a neutron star. Sometimes these are called pulsars. If they're spinning and emitting energy, and if it's supermassive, it'll turn into a black hole, which we actually can't see because it sucks in all light. Rather, we detect it by things around it that it affects. Alright, so for a small to average mass star, it goes like this. Nebula becomes a protostar. That's because of gravity. Protostar, it gets hot enough to start doing nuclear fusion, which changes it to a main sequence star. It'll eventually run out of hydrogen, and when that happens, it expands because it starts to fuse the hydrogen outside the core a little bit. It gets hotter, pushes the outside out, turns into a red giant. After it runs out of helium, it'll fuse things up to carbon. Then it turns into a planetary nebula as it ejects its outer layers. And then the core will slowly fade from a white dwarf to a black dwarf. Okay? Remember, protostar, that forms in the nebula. Main sequence means fusing hydrogen into helium. And once it runs out of hydrogen, it turns into a giant. then can't go past carbon, fades off into just the core. All right, and this is what a planetary nebula looks like. So all this stuff used to be held in place by gravity around this core, but then as this thing got hot enough, it expanded and got pushed this stuff out far enough away that now it's this cloud of gas and dust rather than everything pulled in tight. All right, for a large star, the steps are a little bit different. Nebula still, then protostar, then main sequence, then supergiant because it's bigger, then supernova when it explodes, and then it's got two options. Okay? And then remember, the massive stars are hotter, so they can fuse things up to iron. Then it goes supernova, which just means it explodes, and that actually happens in a hurry, and when that happens, the heavier elements are made, and the leftover thing is a neutron star. Unless it's massive enough, then it's a black hole. Okay? So on a black hole, it's called that because you can't see it, because light only goes into it, not out of it. This diagram shows the relative size of some stars. So these are some red supergiants up here, some red giants here, and here's our sun right here. So when we say it's a small to average mass star, yeah, it's not super big by any stretch of the imagination. It's huge compared to a planet, but it's little compared to some of the other stars out there. Now there are stars smaller than it as well.